Because both or last high when there's the candidate. So if Randy has to be low, but not too close to high, I swear it's hard to start has to be low, and odds are high. And it's high when it's low, and I don't like it. I think your point's off. But I think it works. I think we're supposed to use quite a lot of stuff. I think the problem is not those.
All right, let's get started. Last lecture we were talking about timers. Can anybody tell me the two types of timer modes that we looked at, or the two ways to use timers?
CCR, so compare mode or capture mode?
Yep, so capture and compare mode. One is a way to measure the passage of time, and one is a way to control when events occur, essentially. So we're going to talk about how one of the most common things you have to do in a microcontroller is generate pulse width modulations. There's a lot of different reasons you want to do that. Typically, is you want to control an LED. And just to be crystal clear about that, you imagine you have some LED. Well, you can see that. Okay, wait a second. Stop. Go here. You know how I like Falstad? This is the clock. This clock is doing something, it's going up and down, and there's a parameter here I've changed the control duty cycle. So basically all we're doing for most of the problems here are trying to figure out how to control this duty cycle. So you can see across the bottom, it's changed to a short duty cycle, say 10%, and now we're at 90% duty cycle. Usually we count the on time as the duty cycle, not the off time. And you can kind of see from this example, of course, it's being slowed down way more than a human would see them, but you can control the brightness, the effective brightness of an LED. This is how almost every LED on your electronics is controlled, is through duty cycle. So in this case, it's mostly off, so your eye, assuming this is going relatively fast, over 100 hertz or so, your eye will register this as dim, and then you would increase the duty cycle to have it be bright. Have you seen this before? Where do they teach you in 270? Okay, not this? Where would you have learned this in this curriculum?
Right here.
Fantastic. I'm on time then, not late, not early. Yeah, this is so you also control motors this way. If you want your motor on going particularly fast, you'd send a high duty cycle. If you want your motor going slow, you'd ramp that duty cycle down. From your motor's perspective, it's just getting these little effective current pulses. And then you do it fast enough so that the momentum of the motor kind of evens it out. So it feels like it's getting less current over time. Just like, of course, this example doesn't work for you because it's all slowed down. But when you look in an LED, your eye effectively time averages this over, say, a kilohertz, and you think it's dim when it's really turning off and on. Is there a question? What questions do you have? I can't tell if you're following me or if I'm just going over the basics again.
How bad would it be if we just sent that average voltage to the LED directly without a clock?
That would be fantastic. How are you going to do that?
Directly to...
All right, you got a STM32? How are you going to do it?
You could use a GPIO pin and just send that voltage out.
Oh, I see what you're saying. You want to do this?
Yes.
Fine. Put a resistor there. I just chose 1K randomly. A standard one is 330 ohms, but you could do your no voltage equation, figure out how to limit how much current goes to that thing. Okay, so my question to you is then, what happens if you want to make it dimmable?
You would need a variable resistor. You can't do it.
Yep, you would need a variable resistor. You'd probably want a digitally controlled variable resistor. Surprisingly, those things do exist. They're basically a little, you guys haven't seen I2C buses before, but basically it's a little thing that has a little state machine in it and then has an array of MEMS silicon-based resistors and then switches. The analog connect those switches to those resistors. So you need like an expensive piece of hardware to do it. So we don't want to do that. Yes?
Like traditionally for like lights turning off and on quickly, is that because of alternating current or?
You mean like these lights right here?
Yeah.
So these lights are flickering at 120 hertz because they are fluorescent bulbs, and there's a ballast in there that's going to rectify your 60 hertz. And so now you get two 60 hertz humps giving you 120 hertz, and that's how fast those lights are flickering.
Okay.
It's not what you asked, probably, but
Yeah.
that's why I got excited about telling you. Yeah.
So let's see, so right now, like the lights are flickering.
Yes.
They're going so fast that our eyes can't pick it up.
Correct.
So, like, for example, that's why cameras sometimes put in slow motion on the video, the lights you can see flickering.
Yep, exactly. Any other questions? Okay, so you may not believe it, but this is actually important and useful. So dimming lights, controlling motors, you guys are going to be using it to control servos. So servos are a type of motor that they don't spin continuously. They have a basic little arm that will move usually between 0 and 180 degrees, and you encode the position of where you want that thing to go as a pulse in time. Right, so you set your pulse width to, I don't know, 10%, and it would go 10% of the way there and hold that little arm there. Has anybody seen a servo before? Fantastic. Okay. So a lot of things you can control. One of the things to think about with embedded systems is that, microcontrollers and digital systems are really bad at analog, like real bad. So you need an external digital resistor, or we'll talk about analog digital conversion, digital to analog converters later in the course. But generally it's bad. So we try to almost always encode information in something that computers are good at measuring. Computers are good at measuring the passage of time. Right? We give them crystals, and here now I can control, say, the position of a robot arm. I can control LEDs. I can control the speed of motors by encoding information as time. And that's because we can go so quickly, or going clocks that go microseconds or nanoseconds. We can measure that precisely, but we can't control. We can't do 0.5 volts. That's too hard for a digital system. So you'll just see this coming up a lot throughout the course. Okay. So we talked about how we can set a timer to count up. Now your STM32 has given, and many microcontrollers do this, they've given you all these extra, their peripherals give you all these extra capabilities. It's not like every microcontroller is going to give you a way to automatically generate PWM, although it's really nice, and then you'll be bummed out the first time you find a microcontroller that doesn't do it. You're like, oh my gosh, I have to like bit bang this is horrible. But these are common sets of functionalities you would get. So you can imagine you could have a counter that's going to count from 0 up to some value, and then going to hit that over that auto reload value, and then go back to 0 and keep counting up. So we got these steps going up. And you could have another piece of hardware that's going to come through and basically say, if you're over this value, that blue line, then we're going to turn our duty cycle on or off. So now we can start seeing if you can set your reload time, and you can set this threshold somehow, that you could go and create this waveform down here showing us the T off and the T on, and you're just making this decision basically. Here, the hardware automatically makes a decision to return, and now you're making this pulse train. Okay? There's a couple different modes the STM32 gives you, whether you're in PWM1 or PWM2 mode. It's just which way is the logic that you're thinking about this. Yeah? Say it one more time louder.
Can we change the reference signal ourselves?
Yeah, oh yeah. That's what most of the section is going to be about. You change that to be whatever you want, and that will change effectively. By changing that value, you're going to change the duty cycle, because you're going to turn on at a different point on that slope. So now in Folostat, I just moved a slider around. That slider was effectively changing your reference signal. So we can see an example of that. So here we're saying the auto reload register is 6. The RCR is the repetition counter register. You happen to have it on some of the timer modules on your STM32 you have in lab. Basically, it just says how many times do you want there to be, do you want it to go up to your automatic reload register and re-go. So if you set it to 0, it's going to repeat infinitely. This is just a detail you don't have to worry about, but it gave a lot of people confusion in the past. So we're just going to set the RCR to 0 for all these examples, and it's basically just going to repeat on forever. You could set it to some value, and then that would be how many pulses you're going to send out or how many count ups you're going to do. Okay? We're going to set, from this, you can start seeing the period is going to be set by your auto reload register +1. That's because we're starting to count at 0, counting up to 6. So 0 is part of that count. So here, we're going to see this repeats itself every 7 clock cycles. So now if you're thinking about building this waveform in your mind, you have to make these square waves that are going to be on your oscilloscope. Your AAR, or your AAR is what sets your period. You can also count down, of course. It doesn't matter if you're counting up or counting down. There's no inherent right way to set up a timer to set up a particular PWM. You're going to find there's lots of variables, whether you're counting up, counting down, what your clock rate is coming in, how long you're going to set how many counts your period is. You just have to think about, I have all these levers to pull or all these variables to give me a particular pulse width I'm looking for. All right. So here we're going to go set, so this is an example of going down. This is an example, you can do the triangle waveforms where you count up and count down. These are just different modes. This is center line mode of how we can set up your timer to work. In this particular case, there's a register for this. In this particular case, your AIR sets, not that you return to 0, your AIR just sets your counter to start counting down. So you could count up, down, up, down, up, down. Yeah?
These modes apply to everything that you're trying to counter, or just that specific peripheral?
There are multiple timers on your device, and each one of them will have this or a variation of these capabilities. So you might set up one timer, and then we'll talk about timers have multiple outputs to them too. So you might set up a timer that is just counting up, and then you could have multiple outputs of it with multiple reference signals. So you can set, with one timer, you can set 4 different or n different number of PWMs going off. And it doesn't have to be PWMs. You could also have this be interrupts or other timing events. Okay. So in this particular case, the clock cycle would be 12. Okay, let's go look at the CCR. So here, this is the capture control register. This says some event should occur, okay? So here we have a clock going through. Remember, the clock has, you're going to get a clock from those crystals, and then through that whole clock tree we briefly mentioned, you're going to get a clock signal coming into your module, and then you get some prescaler. You can choose to reduce the clock speed. What would be a reason why you'd want to reduce the clock speed coming into a timer?
Maybe the thing you're trying to compare the timer to is going slow, or going too fast.
So you could, it could be that, if you have a 16-bit timer and you're going off of megahertz, or maybe 100 megahertz is coming in, your timer may expire or wrap around before your event has occurred, right? So you're trying to measure something that's very long, but you just don't have enough bits in your counter to count all the way up to that event because you're going so fast. So you can make a trade-off between your precision at which you can measure an event versus how long your timer can go. So you could say, I don't care about resolution because I'm trying to measure the time between a human touching a button. Well, we don't care if it's microseconds accurate. Well, I don't know about your application. It's probably unlikely you're going to care about microseconds. So you could make the clock going into your timer very slow, and then you could count for a longer period of time. Okay. So in this particular case, we have our CCR set at 3. And that allows us to, depending on which mode we're in, allows us to trigger the event to set the output. So anyways, you get this signal, and then you can route that signal to a GPIO pin. I should have talked about that as one of the options. So you'd have to set your GPIO pin as a particular PWM out, or whatever the peripheral out is, the type of GPIO GPIO pin. So you send it as an output, and then you can imagine this is the output that will occur on the output of your GPIO pin, where you get to, you clock up to 0, you get to 3, it meets that, and then it sets the thing low, and then when you hit your auto reload counter, the whole thing resets, the counter starts counting back up again, and the edge starts going back up again. So from this, if you want to go calculate the duty cycle, right, so it's AAR plus 1 because you're counting from 0, so you have to account for that in there. And then CCR divided by AAR plus 1, and that's going to give you your duty cycle. And your period is just as before, ARR plus 1. Now these are trivial cases. Usually you're counting up to some large 16-bit number. There is a 24-bit counter on your device. I know there is. I don't know if there is a 32-bit or 64-bit. I haven't looked through the data sheet in a long time. But you could also concatenate timers together. We'll talk about building virtual timers where you can keep track of time in software based on a smaller timer or a hardware timer. All right. This would be, this is timer mode 1 up here. Timer mode 2 is just the opposite. Same things are going to occur. Here we're just the polarity of our decision making is opposite. So now you're going to raise the GPIO pin when your CCR equals the current counter count. And then it will reset itself. And here, in this particular example, you just have to keep, when you're doing your duty cycle math, you just have to keep track of what mode you're in. All right, any questions so far? So when you're going through these problems, again, it's helpful to kind of keep this diagram in your head. You have your period, and then you're trying to set your CCR to some particular value to get that duty cycle. And just going through timer mode 2, again, just showing a way to manipulate the pulse width modulation value. So the duty cycle is by changing your CCR. And again, through, if you're going to do timer mode 2, but in the center modulated mode, you could set wider things. Personally, I don't know how often I've ever used this mode. Maybe it's just because my brain doesn't think about it this way. But I'm sure there's good reasons why the fine engineers at STM decided, man, I'm going to make sure that this thing is in this piece of silicon. I guess in this sense, you could go for twice as long if you really wanted to max out your period. You could just double it, but it feels like you could just change your prescaler too. All right. You also have decisions about where the decision made. Is it left edge triggered or right edge triggered? We would define these to you, and they're all defined in the spec sheet as well. Okay. Yep. But what did I really want to get to? Okay. I really want to get to the design example for us to play with. It should be known, just the devil's in the details. A lot of the individual parameters are, you have a lot of parameters, a lot of ones we didn't cover, but it's important just to read through the data sheet as you're trying to set up your register, or as your timer, to figure out all the little details you get to do. You have to enable the main input. There's a bunch of idle and run modes you have to set. You've got to set your capture compare registers. Those we've already recovered. And then just for you guys to think about, this is the block diagram. So we have, what is this? Which timer is this? This is 18. I think it's a general purpose timer. And pointing out here that you have multiple capture compare registers. So you don't have to set up, each timer doesn't have to be its own pulse width modulation. If you can figure out a duty cycle that works for everything, then, or for all your GPIOs, then you can just set up all these, with one timer, you can set up multiple capture compare registers to make decisions. So if you had, say, 6 LEDs that all needed to be a different brightness, or you want to do RGB LEDs, in which you need 3 pulse width modulated waves for each color, and then they get blended in the LED, then you only need one timer to control all of those different things, and those are just pulses that go out of your chip. There are weird cases where, like, servo motors may require, the data sheet requires certain pulse widths and they're not compatible with each other. There's a good reason to have a different timer. Or maybe servos are typically some of the frequencies of servos could be noticeable if you could notice the blinking of LEDs if you had the same period. So those are just some reasons why you might not want to have use all the capture compare registers in one timer module. Okay, so we're going to go to a worksheet next. If you have any questions about setting up pulse width modulation. I think it's general confusion because you haven't done one yet. Is that what I'm hearing? All feels foreign? All right, let's do it then. We'll learn through practice. So here's your problem. You're given a timer module, and you need to go figure out what values you need for CCR and your prescaler and all those sorts of things. So there's multiple answers to this. There's no right answer. Yep. Thanks. Did we run out? I think that's 3. Thanks.
Thank you.
I mean, we can also be pretty cool. Okay, right after this class, and then we don't have to eat it, right? Just grab the food and eat something. It's also nice weather. Also, it's because I want to say at least the dinner menu. Yeah, sure. I'm sure they won't be able to consumers. That's like ARR and CCR. I don't have to understand. I understand. This is capture compare register. What is ARR? So auto reset.
What is it?
It's the reset.
Auto reload, right?
Auto
So
reload.
when it gets to here, what's it that you're trying to define this point right here, basically?
I just wanted to know that I struggled with this yesterday while doing the lab. It was not fun. It's like, what the hell is this?
Should have gone to GPT.
I should have, bro. I should have just asked you.
What is ARR?
What is PCS?
Prescaler.
Prescaler? Or PSC, sorry. What's CCR?
That's the
Capture
pair there.
Yep, okay.
It's where the line is.
Great.
Okay, so I want, what is prescale? Prescale to make it slower.
Prescale makes it.
Okay, so right now I'm at 16 megahertz, and I don't want to be at 16 megahertz. I'd rather be at not 1 megahertz. I'd rather be at 10 kilohertz.
What's that value?
Oh wait, no. 10 kilo. I need to get 100 kilohertz.
It's going down.
So I want 160.
I just don't know what it is.
That's just.
So the ratios for counting
One over.
So we don't want it here. We want the duty cycles. We want the duty cycle. This thing to be as so we don't actually want that.
Bro,
No, I refuse.
Bro, I was sleeping over this one.
Wait, my prescale is 160. Yeah, there's only a 100 kilohertz clock, right? And then with a 100 kilohertz clock.
Oh, yeah, well, I'm not saying we should have a prescale.
Oh, okay.
Yes, you are right.
Do I want a 100 kilohertz clock or a 10 kilohertz? 100 kilohertz is a lot. Oh, and it's also freaking. It's 6. 6 is so annoying. Okay, I don't want a 100 kilohertz clock. I want a 60 kilohertz clock. Wait, how is this possible?
Wait, how's it doing cycle 10%?
How do I get a 10% on the 6 clocking? Huh? It's locking up to 6. Oh wait, no, I can tell it not. I can tell it to lock higher, right?
Oh, wait, actually, we're supposed to.
Wait, do I need to make a walk up to 6? If I make a walk up to 10, then we're chilling. Wait, I want to make a walk up where I'm gonna have 1 high, 9 low. What? Yeah. So I need. I can change it to make it not walk up to 6, right?
Yeah, that's just an example. That waveform is not what you have to make. You can make anything you want. Waveform is just an example. Well, 0 to
5, and then I just get 5 triggers. 0, 1, 2, 3. Oh wait, I just used 4. I walk up to 4 and trigger on 4.
I'm a little confused. I want to modify the clock to get a better attendance. I'm a little confused.
what's that grayscale do?
Yeah, so divide the clock. Okay, let's divide this.
I think it's prescaler plus 1.
And then I can modify the count. If I want 10% lead.
1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, I did it. ARR equals 2. Yeah. CCR is going to be 5 as well.
There you go.
And then I need to figure out what market.
Input is your
I need my clock.
no, like this is your frequency. It's going to prescaler plus 1. Plus 1
I need my clock to be right now a second. I read kilohertz. So you need less than 16 megahertz at 1 kilohertz speed. Okay, to slow it down.
Yeah, you can slow it down by some division. It doesn't have to be the power. It doesn't have to be a power too.
Oh, good.
So the trick is the prescaler is prescaler plus 1. Yeah, just because of how the prescaler works. You put a 0 in the prescaler, no clock comes out. They always demand that 1. So it's whatever value prescaler plus 1 is. There are many multiple.
So it's going to be high for what? It says right here. The timer output is high if the counter is larger than or equal to PCR. What the heck do you use your command number? I just use Wait, I don't know if prescaler gets it. But they didn't say anything about it, so this one. Yeah. I'm not sure if this is a good one. Why is it? They should have a cycle called outside. It resets with classics here.
And there's a slide.
Here, it's constantly high when it drops down to 0.
I think it's just a difference between this mode and this mode.
Manual lap on this. Great. 8 times the support fix. I don't know either. Also, we have seen AR arbitrarily set value.
How is my diagram?
So looking at this is a lot of it.
So that should be the question.
I don't care.
So, you guys do 10%.
It's true. Wait, what's 16 layers? Let's go over
Oh, look at this. This clearly I count up to 5 and then go back to squats. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's I'm losing it. I don't believe this lie. I'm falling out of love with this lie.
Yeah, that's just what we are.
Yeah, there's a lot of options. This is what I have, but it says that the duty cycle is 1 minus CCR over 8R. Which means that this theoretically doesn't work, but I'm looking at the diagram. Exactly. That's not 5. That's 5 is for the next 4. So yeah, why should it's 10? So that seems like it should work, but the duty cycle formula is just like yeah, they can both work. That's why I don't understand this formula. This type of duty cycle is 0. Like, really, you would need your CCR to be larger. Let's do a comparison. It's like, all the other ones.
And then ARR is just how many.
CCR. Well, I'm just applying the math.
It's 1 minus CCR over 8R. But this is the thing I was trying to do. Like my clock, my timer goes from 0 to 5, and then it triggers only on 5. Or no, it's like it goes up like this. This is the one that's high enough, and then it goes back down. But according to this formula, that gives you a duty cycle of 0.
That's why no one uses it.
Because this would be one that, right? They have my Wi-Fi, and then I go from 0 to 5.
Really,
I'm off the beat. I'm doing 3 scalars. get one. Prescaler has to have a +1.
Well, yeah, so prescaler plus. So that's why my prescaler is 150.
Is it a 158?
That would be, yeah,
Oh,
I
is it?
want, so it's a 160.
Oh, that makes sense.
I know, I forgot. I love having an early lab.
Because it's just a fine randomly to have a +1 over there, because otherwise if your prescaler is 0, you're just fighting by it. Go back up, bro. Go back.
Here, I'll just show you what I'm
Make sure, you have to be sure that 10% capacity is heating.
So for example, if I select this one,
You can figure out like,
You just subtract 1
you have
from
your steps
what you
up here,
actually
right?
want. Like I want to divide by 60,000.
I do.
I don't get it. Why does the formula
Because it could- you could choose-
looks right for the cases it's showing? But over here is clearly wrong.
Yeah,
Wait, is this actually is this a half moon cycle? Trigger 1, 2, 3, 4, 5, 6.
yeah. And there's one, like a few sets will be perfectly achievable. And then you come back and you say, well, does it really matter if it's 10.1% or 10.2? How are you doing? Good, yeah. I'm just checking the formula.
How come it only likes 3 on the rising edge? It doesn't like 3 on the falling edge? I don't believe what? Yeah, that's why my thing doesn't work.
Oh, yeah, it's a bit curious.
How are you doing?
Huh? It's a comparator. It doesn't care.
Well, apparently it does.
It's like our kid died from abortion coming in for 2. So my
From these two formulas.
So yeah, the same. Here, this is high. So this is why this doesn't work.
Yeah.
This high triggers on the 3 that was frozen.
I think if it's
All of
particular
the
mode,
3
it's
is
not
low.
down, down, so that would make it.
I don't know why.
And then your prescaler got to be prescaler plus 1.
Well, here it's also rising edge. It's rising edge and it reaches 3, and then it goes low. Here it's a rising edge and it reaches 3, and it goes high. Well, actually,
Is this how, in your theory,
okay, it doesn't work because of J. That's the answer. So instead I have to do what you did. Instead of 1599.
6 out of the,
No, I don't know what I need to do what you did. I'll do. It's basically how long instead of what you use. Okay, so I'm now on
so we don't,
10 kilohertz.
you want to get close to
10 kilohertz on as a period of
1%.
okay.
All right, does anybody want to share the answers they've come up with?
Yours is 1,000 and 900, so mine would be 190, right? If I want to fast cycle.
I know somebody's come up with the answer. Do we have more time to work on this? Does anybody want to share their answers then? No, there are multiple answers.
So,
Well, how about this? Actually, how did you approach the problem? Let's start that way.
well, you kind of have to decide what's going to give you the number of increments in that 10 millisecond period that you want, and you can do that with a different combination of prescalars and ARR. So I figured if we want a duty cycle of 10%, we want something where we can, if we want our clock to be able to hit that on like 0.1 of whatever our total like count is. So I picked a prescaler of, or I wanted a clock of 10 kilohertz. So that gives us 100 divisions, and that leads to a prescaler of 1599.
Why is it 1599? That doesn't sound like a multiple of 16 megahertz.
Because you add 1.
because of those awesome designers, right? Prescaler is whatever value you put on there plus 1. And I believe the answer, so that's your division value. And I believe that they've done that is so that you can't accidentally put 0 in there and stop the clock from coming through. I think that plus 1 is just an arbitrary choice by the STM32 designers. Anyways, go ahead.
Yeah, so we picked a prescaler of 1599, and then using the equation that we got from the pre-lab, which is like the period of our PWM is 1 plus ARR over the frequency, then we got an ARR of 50, or with 40. I got a little confused with like the up-down.
Yep.
My final answer ended up being PSC of 1599, ARR 50, and CCR 45.
Okay. Now, does it matter if you guys got exactly the same CCR and AAR? No, because there is design choice here. It's just that you'd have to have a ratio, depending on what your prescaler is, that would give you a 10% duty cycle. So there are multiple answers to this. Did anybody find a radically different approach or different way of looking at this? Or have concerns? You could be wrong. Yeah.
I have a question about what's considered high on the CCR. Because I was originally doing PSC equals 15,999 to get down to a 1 kilohertz clock.
Yeah.
And then 1 kilohertz clock would have a period of 1 millisecond. So then I would have an ARR of 5, so that every single period I have 9 steps.
Okay.
Or 10 steps. With CCR equals 5, so that it would trigger on the very top.
Yep.
And I don't understand if 5 would trigger or not, because the formula we have for duty cycle suggests it doesn't. And the diagram, like this one,
Yep.
for some reason OCREF is high on 3 when it's rising, but it's low on 3 when it's falling. So I don't understand what the comparison is doing.
I think it's whether it's going up or going down. But I'm not going to give this demo anymore with high up and with triangle waves because I always forget how it works. But I believe that on rise, as you're going counting up, it's when this equals that, and then it's going down when it hits that. That makes sense. It's your perspective. Does that answer your question?
Kind of.
Okay, so what happens here? So it should go up and then down immediately, right? Or nothing happens. One of the two. Goes up, and then as soon as it goes to 5.
Like I'm thinking it would never turn on.
It would never turn on. Yeah, your formula says 0 duty cycle.
The formula says 0, so I was trying to figure out why.
I think that is right, because it would turn off as soon as it turns on.
Right.
So I think that would be 0. Okay. I think we logicked our way through that one. Any other questions about this? Yeah.
Just like going off what he said, that's what I attempted first too, and I originally started with a 1 kilohertz clock, and I had to go to 10 kilohertz for that reason. So is there like a threshold? If our period is 10 milliseconds, then like do we know we need like more than 10 divisions for that reason?
Well, I think it's the peculiarities of if you're actually at your AAR or not, right? If your duty cycle equals your AR, then there's probably a problem. I think that's so by increasing the step sizes, you avoid that problem. Yeah.
Is there really like a reason to just use the staircase versus the increment decrement versus increment 0?
I can't think of a good one. I'm sure I've probably been faced with a problem that was like, I can't get the math to work and I would need that. I bet it's common enough. But that's typically not how I would do it and not how I think about setting up PWMs. Maybe it's more of a misnomer. I think in the future I'll rewrite the problem so it's always in mode 1. But I don't think it helps learning maybe. Maybe that's what I'm learning now. Yeah.
I have a question kind of following that. Like, is it resource intensive to like turn it on and off? Like, would that be why a triangle's better? You just stay on for longer?
Well, you can get double the count out of your register, right? So you can basically go twice as long. So you may have some point of view where you're like, I have this clock, I can't change it. I can't change my prescaler for some reason, I don't know. And I just need to go double. So this would be a way to get you longer period of time. It may be that the math that you're doing, I don't know, in C-land or something, just happens to be that like how you pose the problem is better posed at this sort of structure. I can see that being the case. All right. Let's go on to the next. Well, is there any other questions? Those are all good questions. Yeah.
I'm just kind of confused of how CCR and AR were calculated, because I get the PSC.
Yep.
I'm still a little bit. I keep doing it and I get like 88,000 for my CCR.
Well, we can go through the math in office hours or after this class if you want to just go straight math. But do you understand how they're helping to make the waveform? Okay. So yeah, we can just go through the math then. I don't have the answers on me for this particular one, but I'll put them on Piazza. Okay. All right, let's talk about other timers. It's important to think about just because these are built into, SysTick is built into almost all STM32s or all ARM processors. So basically this is the, we already kind of covered what timers do, but this is, SysTick is system clock basically that is built into almost all ARM processors and part of the ARM spec. I guess it's possible to have one without it if you had some like little ARM 0, but it becomes an integral part, and it's something that you can set up interrupts on any of the timers, but this one is directly involved in having real-time operating systems. So if you want to run an RTOS on STM32, which in my brain, I was like, oh, all right, this is always bare metal programming. I get to control everything. And then you're like, oh, I actually want to do something advanced and not have to write every code for myself, like have a Bluetooth library or a Wi-Fi library or something. It's hard to set up. Having an RTOS is actually a great idea. And they have them on little microcontrollers, even smaller ones than the one you guys are using. So for an operating system, you need some way to set up timers and interrupts. And this is the built-in function for your device. So it's part of the spec. It lives inside, this particular timer lives inside of your ARM Cortex-M processor. It's not necessarily part of the peripherals, but you do get access to it if you wanted to it. So this is like the basic timer that you will always be able to rely on. This one is, let's see, where it's 24 bits and it only counts down, if I remember correctly. Other than that, it's, you can set up interrupts off of it. So just like before, it doesn't have a capture compare register necessarily. It's just a down count timer, 24 bits, and it's going to set up an interrupt after it gets down to 0. You can go through the false set if you get excited, but basically it's not much more complicated than a bunch of D flip-flops and AND gates that consecutively count down. So it doesn't take up a lot of processor space. Okay. So here you're going to go through, you're going to set your reload value. In this case it's 6, and it's going to keep counting down, down, down. This will be able to set up your periods this way, and then SysTick will go off, and you can, again, have an interrupt as a result of that. There are a bunch of different, there's a register just to control this. It has a bunch of different control modules. So here you can enable it. You can enable the interrupt. You can tell it, you have a couple of choices for clock sources. And when the flag goes over, this register will be updated, okay? And how that works, oops. I mean, it's pretty basic. You get an interrupt if the count flag has gone off, meaning it went down to 0, and the tick interrupt register is set high, then you'll get a SysTick interrupt. Just likewise, you can select 1 to 2 clock sources. There's a clock divide by module that you can set up somewhere else. It's divide by 2, 4, or 8. So it's not a prescaler, it's a clock divider. You get your AH bus clock coming in, and then you get to control which source it is in. And so if you collected a source, and then you just AND it into this AND gate, which enables this clock or not. All right. There are 4 different registers. We just went over one of them. It's good to know what they want, or that they do. This particular one is actually kind of unique that they would give it to you. We'll talk about that in a second. So we have your SysTick status register. You have your reload value register. You have the current time, right? So you add a register. You just want to know what the current time is. You can pull it out of that register. So reload, 24 bits. If you put a 0 in there, it's going to be disabled. You can put, up to 24-bit values in there, and it'll tell you what you'll be reloading every so often. You got the actual value of the current timer you can pull out. So you could just say how long between certain events of curtain have happened. You could instrument your code even and say how long does it take between this thing, and shove that into some register or some memory location, and just be able to benchmark your code without necessarily using the debugger. That's an interesting way of doing it. This is important. It says it's randomly set. There's a random value set on reset. Why does that say that? Why is there a random value in there on reset? Yeah. Well, that's kind of an interesting point. I hadn't thought about that. Yeah, I don't know how long it's been running. Also, when you just boot up Silicon, right, you're going from 0 to something, you don't know what value is going to be in your D flip-flops, right? So you'll find that it could be, especially like memory, like unallocated memory just has some random value in it on startup. And so you can find out it could be some random value in there that you don't know what it is. Now, you might say, oh my gosh, all those cryptography people have been trying to make random numbers for a century. We just found the source of random values in here. We find out it's not actually really random. It's random per chip. From one chip to another one, it'll be random. It won't be constant, but it won't have enough variation to be considered truly random. It might be that some bits are a little bit more variable than other ones, but in general, there's a group of numbers that kind of clusters to in a way that's not truly random. Okay. And then you have the SysTick calibration timer, register, which is a register you can go to and get the value out of it that will equal 1 millisecond. So there's an offset value that they're going to give you, assuming that your clock is at a certain value, and they'll say, okay, here is if you want a 1 millisecond or 10 millisecond timer, and this actually is unfortunately, the STM32L that you use has a value, the reset value, or the 10s millisecond register gives you 1 millisecond, but other STM32s give you 10 millisecond. Anyways, that's the detail. It's just saying, if you want to precisely be able to count the passage of time for 1 millisecond, you can pull out the calibration value, and that's the value you need to go and put into, say, your reload, and then you'll have a timer that goes off or interrupt that goes after every millisecond. So you don't necessarily have to do all the mathematics to figure out what that value is. You can just pull it out of that register. Does that make sense? Does anybody think that would be useful?
Is it always just 1 millisecond?
This is what they're trying to do for you. The designers are saying getting 1 millisecond or 10 milliseconds, depending on which piece of hardware. That's the painful part of this. STM isn't consistent. You just get this value out and put it back into your reload. You just basically store and load, or load and store, and now you have a timer that's going to go after every 1 millisecond, or interrupt that will go after every 1 millisecond. So it's just good. They're trying to help you with some housekeeping, timing things to make your life a little bit easier. All right. Calibration code. You guys are more than welcome to walk through all this code. It is super great. All right. Well, let's go back to the other presentation quick. All right, so wrapping up timers. The big things I want you guys to think about here is think about where time comes from. It's not just that it appears on your processor some way. There is some physical thing you have to measure the passage of. and it happens to be these crystal oscillators or these MEMS resonators, there is some physical thing that's vibrating that we're keeping track of. That's about as much as you need to know for this class. It's just know that it comes from physics. There are all these different ways to get clock signals into your device, whether it's low frequency clocks, high frequency clocks, internal clocks, or the PLL. Just know for your projects, it's a very flexible platform that will give you whatever timing you want. We talked a little bit about clock distribution. It's good just to know that it exists when you're looking through CubeID and you want to push one of those clock values somewhere else. This typically happens when students are trying to interface with some weird hardware, like you're trying to make a VGA controller so that you can, play images on a computer monitor. Or people have tried to do HDMI as well. That spec requires very specific timing, and it's easier if you get your clocks to the right value. It's good to know the difference between prescalers and clock dividers and how prescalers, what they do for you, and remembering that they have that +1 in there. Then the other parts are capture and compare timers, knowing the difference in when you would use them. And there's a lot of work in in your lab, and in general with being able to do pulse width modulation, that sort of stuff. So before we go on to the next section, what questions do you have about timers? We could go back and review any of the slides if you would like. Either it's perfectly clear or super bored, a little bit of both. Yeah.
I guess just like sharing our prescaler values, those terms like how precise we want to be, and then everything else just kind of follows.
Yeah, if you're setting up a pulse width modulation, you want to figure out, I guess the parameters are how long does the period really have to be? How precise do I need to have this? How many steps do I need to have? It's generally in the real world, it's easy to have lots of steps and nobody really cares. It just becomes a problem until when you're like, oh, I just can't go long enough because my counter doesn't have enough bits in it. Yeah.
Can we save power by having less steps, or is there no difference?
I don't think there's any difference. What are the things that would care about? Having a module enabled and a timer going. Once it's going, you're burning the power anyways. And so everything after that is just a decision of how you're going to use that data, but the thing's already running. So you would save more power by having one timer going and multiple capture compare registers making decisions on that timer rather than having multiple timer peripherals on and working. That would be a big savings. I say it could be a big savings. I know it will be a savings. I've never gone on a power meter and measured precisely what peripherals consume what power though. What other questions? Yeah.
Where are the updated slides?
What's that?
Where are the updated slides?
I thought these slides were on, they're not up there?
At least not the last couple.
Oh, okay, yeah, that's fine. I didn't know if we were going to get there today. I will put them up there. You will have them.
Okay.
Fair question. Yeah.
Can you explain how PLL works again?
Oh boy. So PLLs, phase lock loops. The fine folks in ECE, there are people still getting PhDs about PLLs and making great PLLs, fast ones and low power ones. It's a whole subtopic of study. In the purposes of this course, PLLs is a way to take a slow clock and turn it into a faster clock. Okay? And the trick for that one, the way to think about that is the example if you have a child that is swinging quickly, and I'm a very slow, human adult trying to push my daughter, and I push every other time. And so she's going twice as fast as I'm pushing, and we are going to be perfectly phase aligned. We're going to be locked if I meet her at this exact moment every other time. And if she's going a little bit faster than me, then I'll miss, or I'll start pushing too early. Or if she's going a little bit slower, then I'm going to push too late, I guess. And then that will, the lock loop part of that word, phase lock loop, is I have to be in phase with the child, and I lock in the sense that if they measure the rate, if I'm early or late, then I would change my timing to adapt to whatever frequency she's going at, or vice versa.
Swinging tile, the
Yep.
faster or the slower?
I guess it just depends how you're going to talk about it. Let's say that one's fast. That goes twice as fast as I go. So I could make, I go at 1 hertz, and the child now can go at 2 hertz. The child could go at 4 hertz. Yeah. Or I could do some dithering or some, there's lots of little techniques. I went too far in that example. Let's just back it up. PLL all it means is you take low clock and make faster clock. Yeah.
Can you explain to me what like a scalar kind of does?
It divides the clock down. Yeah, it's the opposite of the PLL. PLL has a lot more magic and control loop in it because it's not an easy division of something. Is this the one with it on here? Yeah. So here's your prescaler. There's your prescaled value. Your clock goes in. You get this value out. And basically inside here is just a little counter that's basically going off and then setting a rising edge when you've hit that value. And so that's why you can divide by some value, if that makes sense.
Why is it important for us to pass the clock through the prescaler?
So you have flexibility. Otherwise, you would only have one period you could ever do for a 16-bit timer. Or sorry, you have a maximum period that's not adjustable. So if you're going to 100 megahertz here, the longest period of time you could go is 16 bits times 1 over 1 megahertz or 100 megahertz, whatever. Does that make sense? You could not measure a long period of time. Right? So this allows you to slow down your clock so now you can measure longer things.
So like human interaction.
Or just, yeah, or to some value. You wanted to go 50 milliseconds because you wanted some RC discharge to occur or something, and you wanted to measure what the value was or something. It doesn't just have to be humans, but slow things compared to the core. What other questions you got? All right, we'll go on to virtual timers then. Fantastic. I didn't think we were going to get there. Give me a moment. Oh. All right, just a reminder, because I forgot, this is left over from last lecture, last season, and I forgot to say it. On Thursday, your ideation slides should be due. Some people said, I have no idea what I'm supposed to propose. This makes no sense to me. It's too open-ended. You can go through the project proposal and kind of get an idea. Basically, it's don't worry about hitting the criteria of the project proposal. Project proposal, like you have to show competency in core embedded systems things like memory mapped I/O and interrupts and serial communication and ADCs. You don't have to do all of them, you have to do some of them. You should more think about what's the cool embedded systems-esque thing I want to build, whether it's, last year we had alarm clocks that would go off and try to run away from you because people were trying to wake up in the morning and they just hit snooze all the time and they wanted a robot that would run away from them. That's actually a Kickstarter project. I'm sure Xiaomi's made it by now. That's fine. Go try to make that. You'll get feedback from us on how feasible or how hard it is. I've seen projects where people wanted to make an extra opposable thumb, right? So when they can grab things in weird ways. We had a quadcopter wall crawler thing that was basically a car that would fly up against the wall by sucking itself with a fan blade to the wall and to the ceiling. It kind of worked. The other thing is they could I told them there's a Amazon product you can buy that does this. Now, I'm not going to give them credit for what they bought from Amazon, but they could go and put an STM32 in there. We have smaller dev kits, make it wireless, and add all this extra functionality to that dev kit that exists. We almost always have some wheeled vehicle that plays some version of Mario Kart, and you go over power-ups, and you go faster or slower. Usually some sort of tank thing that occurs. Personally, I get bored of fish tanks because it's really hard. Like, how do you test something that's supposed to happen over a week's period of time in like a 5-minute demo? That can be hard. Anyways, do people have any questions about the project? Yeah.
Is it an issue if we like theme our ideation slides like a stupid theme, like a Roomba?
If all your ideation slides are Roomba related?
Yes.
I'm grading that you started thinking about stuff you want to build, so that when you come to the project event, team formation, you have something to talk about. Yes.
Very important question. What happens to our projects after the course? Do we get to keep them, or do you?
That's a good question. Project materials are the property of the University of Michigan. So, however, if you really loved your project, you just loved it so much, and you're like, I want to buy the servos for this myself, I'm not going to stop you. I'll discourage you, but I'm not going to stop you, and then you can have your magical widget for yourself. There are things like, I don't want to recover wire, right? Just like random wire that you use. Like some things we're just going to be like, nope, that's garbage. But usually the valuable parts, and Matt will give you a bunch of parts already, like STM32s and Wi-Fi chips and Bluetooth chips. He'll give you those stuff, and we'll need them back. Yeah.
This is just idle curiosity, but does the IP belong to us or the university?
That's a fair question. I think, for undergrads, it's different than graduate students because you're not employees, so I think you retain rights to your IP, intellectual property.
No.
Good luck. It may be that the university also has rights to your intellectual property, that it's not. So if you really care, you should probably figure that out beforehand. But undergrads generally get more rights than PhD students because PhD students are employees and the university retains all their intellectual property. I used to be in industry. I have lots to say about intellectual property. We can have a whole lecture just on that. What other questions do we have about the project? Yes?
Make 3 slides for 3 projects or 1?
3 individual projects. Just an idea. Just because the problem is if you just do 3 slides on one, then you've only thought about one project. And if you can't get a whole bunch of people to come and work with you on it, then you haven't thought more expansively about all the projects you might want to work on. So the goal is to get you to think about projects that you would want to work on. The criterias are an image, less than 100 words, your name, a descriptive title. Yep. Yeah. Yep. We'll serve you pizza. Yeah.
Can we request pizza? Like what type of pizza?
Oh my. That's. She's. So, go put a poll on Piazza. Go enjoy. I don't know about Pizza House. I haven't thought about where to get it, but. I see the high bits are being gone off first. Any other questions about the projects? Okay. All right. So talk about virtual timers. We went through capture compare timers. Fantastic. Let's talk about virtual timers. All right. So describe to me some way that if you wanted to count for years on your microcontroller, what would be a plausible way to do that?
Press go and never stop.
Well, but you only have 16-bit timers, and your clock only goes so fast.
I would use a counter that when it finishes, I use another counter and that's gone. And that one to other counter.
Wait. So in softwares, I think is what you said. What did you say? Say it again.
So you have the clock as a counter.
Yep.
When this counter runs out of memory,
Yep.
it enables another counter.
Oh, and a whole nother clock.
It adds a 1 to another counter.
Okay.
And when that counter finishes memory, it adds a 1 to another counter.
So what happens if I only have 16 counters, though, timers on my device? What do I do then? There's some limit there. Are you figuring out how many bits I need to count to the end of the universe? Yeah.
Use like a prescaler that's like super long.
Ooh, super long prescaler, like the passage of the sun's prescaler.
So like you have your counter, and once you reach the top of your counter, you like increment a value in memory. So and then you basically do that a bunch, and then however many you need to for.
Okay, so basically we'll have some software, some C on top of this piece of hardware.
Perhaps we'll call it a virtual timer.
Yes, yes, you've seen where we've gone here so far. What's going to be the challenge if you wanted to have lots of virtual timers? What sort of problems do you think you're going to start facing?
They're out of sync.
They're out of sync. So I have one timer, and I want to keep track of lots of different things in software. Yeah, okay. What do you mean by out of sync? Tell me more about this idea.
Well, so the question is, what happens if there's a lot of timers?
I'm trying to do all these timers in software. I have one hardware timer. I have lots of software timers I'm trying to keep track of. What's the challenge occurs? Because he described a good way to keep track of one event. Sorry, I should have said that, one event. But what happens if you have multiple events you have to keep track of? Yeah.
You run into the same issue where you run out of space on hardware to keep track of the virtual.
Okay. Right, so I guess in that sense, we're thinking you could have one timer for each long-term event you want to do, right? And then whenever that timer goes off, you increment something in the software to keep track of how many times that timer's gone off. But then you're still limited to how many timers you have, hardware timers you have on chip. Okay, what's the way to overcome that? More hardware timers. You can never have enough. All right. That's essentially how this works. How many timers? Enough. You can never have enough timers is essentially what industry has figured out. Timers, I mean, it also just depends on how complex your system is. If you're trying to do a single function, relatively easy embedded system, obviously there is enough, but or there could be enough. But as you get larger and larger, more complex, especially if you start having user-facing things, even if your interface is just a couple buttons that you have to program your VCR. You guys don't know what that is. Whatever. What do you program with buttons these days? I have no idea. What doesn't have a Bluetooth interface? I don't know. You have little alarm clocks you probably have to turn with a timer. Keeping track of those things is good to have more and more timers. So we've talked a little about this, handling it in software. We've basically already brainstormed through that. So let's go through a simple example. So maybe you have 10 events. We want 10 of multiple events you want to generate. We have to keep track of. You have one hardware timer. You have to keep track of how often these events are occurring. So you could say, here are some events I have. I have in 10 seconds, I want a timer to go off, 3 seconds, 20 seconds, and 43 seconds. So the easiest way to get to the 10 seconds is I set a timer. I do all my configurations, my PCS or my prescaler. Let's say we'll choose one prescaler for the whole thing, and say we're going to set our auto reload register to go off after 10 seconds. We'll make it easy on ourselves, and then we'll have some interrupt that goes off. Okay, so we're going to count up to 10, and then so say 10 goes off. The way you would handle this is you'd have an interrupt, and then you say, okay, well my event 10 has gone off. I've gone for 10 seconds. I do whatever my interrupt handler tells us to do. Then I would go through all the rest of my events, and I decrement them by 10 seconds. So now I know since I last was in this loop, 10 seconds have elapsed, therefore I have 3 more seconds until my 13 second, 10 more until my 20 second, and 33 more until my 43 seconds. And so you're keeping this list of all the current state of the timers, when their goals are, and then whenever time you enter that loop, you're going to decrement by how long that timer you've set your hardware timer for. So again, we go through, what are we going to set our timer for this time? 3, yep. We're gonna go through, we're gonna set 3. We're gonna go off, when the timer goes off, you're gonna do whatever was required when timer 3 goes off. You're gonna go through, you're gonna decrement your 10-minute by 3, your 10-second, and your 33-second by 3. Give you that value. Set the next one for 7, and go off for 23 seconds. Then that's your last thing on the queue. And so now you're just gonna count for 23 seconds, and then you'll be done. What we'll talk about next lecture is what happens when you have different events coming in, when you have new timers that have been created, when you have how you keep track of all these different things, all those extra edge conditions. And these concepts will be more important for 473 if you choose to go to 473, because then you'll be writing yourself or working with an RTOS and understanding how these event timers work. All right. I think with that, let's see. Oops. So some of the problems here, you're only working with compared timers, you're not doing capture timers. Some of the challenges here is that your ISRs may not be particularly precise, because now you have to have an interrupt. You're going to endure some latency. Does anybody remember how many cycles of latency you endure for a ISR?
12 or more.
12 or more. Very good. So now you have to endure that. Plus, you're going to have some software overhead, because you have to do some sort of, even if it's less than 100 lines, it's going to consume some amount of time. So it's very hard to do precise timing with virtual timers. So you have to have this mental division of precise things that need to occur happen with hardware timers, and imprecise times can happen with software timers. Yeah. But then for long-term human scale things, it's not really that important. Okay, so we'll end there, and we'll go through an example of virtual timers next class. Oh, and hand in your worksheets to get credit. Thank you. Yep. Oh, yeah.
So it says in this question.
Really? You like the
Just
fidget?
devices, but also.
General images.
Specifying that. When I use, when I use like this should be, I don't have to use like separate, like deeper.
Oh, what are you trying to do over here?
Like I'm trying to shift.
That's interesting. You can do it that way. Yeah.
That's
I think you're trying to keep track of H cycles.
yeah. So it's fine if I use 2.
Yeah, why not? I like that.
So, in your project, you can put contents in the context of a bigger project.
Yeah, we've done that in the past, but I got to be clear how it solves a 373 problem.
Right,
It's got to be clear whose work is on it.
right.
But-
So it has to be like separate from the work that other team members understand.
Yeah, or at least you have to be able to demonstrate that you have done your part.
Right.
So what are you thinking?
So I run one of the project teams, Supermodel project team, so we make competition cars, and I wanted to do like diagnostics, like temperature sensors, voltage, current, like that.
That sounds reasonable. I guess the questions are, we've done projects like that in the past. It turned out well, so we'll support that. I guess you have to kind of figure out,
I just want to.
are you going to do, is this going to be trying, like, this is one of those rare cases where we would allow you to be solo because you actually have a bunch of other team members. But if you can get people from the class, that would be great.
And financially, would I be able to use team funds?
Yeah, I don't care.
Okay, so I can just boost the budget, basically.
Yeah. While still keeping within the scope of the class, yeah.
We had a question about our lab grade.
Okay, here we'll step out for these guys.
Thank you.
Okay, so let's get this table, like it this high as a, no more, You know, the
overhead
projector.
That's cool, they got a camera.
Yeah, they got a document camera, and it's gonna be recorded. Oops,
It all gets recorded?
yes.
Oh, great.
That's okay? You probably.
No, without an, it's too, yeah, it's too small.
Yeah, your voice, I don't use it.
Yeah, I don't know.
Some of the crews need it.
Oh, really? Because they can't project?
No, but you're gonna do fine, and, now, I gotta get, oh yeah, hold on, I gotta get this set up. What we do is, the phone's over here.
So you just want me to sit and then I'll get up?
Yeah, I'll introduce you. Or you can walk around, you can do it there. I'll introduce you, then